Good morning, everyone. We'll get started in just a minute or so. We'll let more people join the webinar. Okay, we'll go ahead and get started. So good morning, good afternoon, everyone. Thank you so much for joining us today and welcome to the Hive's Think Tank webinar series. So my name's Olivia, I'm the operations manager at the Hive. We're really excited to have you join us and hear from our portfolio company, Geminis, Schlumberger, and then also from the University of Michigan, the aerospace engineering team. So with that being said, I want to just quickly go over some of today's best practices for today's webinar and really share what the Hive Think Tank does. And then I'll pass it over to Ravi, the Hive's founder and managing director. So we do love questions. So we love for people to use the Q&A button instead of the general chat box at the bottom of your screen to ask our presenters any questions, which they'll answer kind of throughout the duration of the webinar. It's only going to be an hour long, so we really appreciate you joining us today. And then just so everyone knows, the session is being recorded and will be available to review later on today on the Hive's YouTube channel, which I'll link in the chat box. So the Hive Think Tank is an ecosystem of thought leaders, corporations, and entrepreneurs. So we're an event and content platform with a focus on AI, 5G, blockchain, Web3, enterprise, health, and so much more. We do host events almost every other week on cutting edge topics in technology and business. And then we do also publish corresponding written thought pieces on Medium. So I'll share all the links in the chat below, but to stay up to date on everything, make sure to join our meetup group and then also follow our Medium page for any content. Yeah. And then just quickly, I want to thank our sponsors, TIPCO, Avanta Ventures, and Gamuda for their support. And for our audience, if you are interested to get involved with the Hive Think Tank, feel free to reach out directly to me. My email is listed right there. It's at olivia@hivedata.com. And then make sure you're also following our social media pages and feel free to tweet or share this on LinkedIn as well using the hashtag HiveData and at HiveData on LinkedIn and Twitter. So just one last thing. So in about 2 weeks, we are hosting another webinar around the future of the enterprise with Nelson Petrosak, who is the global CTO of TIPCO, Blockstream, which is also another portfolio company of ours, and also alongside Kamesh, who is our chief product officer at the Hive. And just a fun fact, Nelson is also releasing a book in the next couple of weeks about blockchain. So we're super excited to have him on the panel alongside Blockstream and Kamesh. So with that, I'll pass it over to Ravi to introduce our speakers and to share a little bit more details about the Hive.
Great. Thank you, Olivia. If we go to the next slide, please. So a little bit about the Hive. The Hive is an early stage venture capital fund that is focused on data and AI-based companies, largely focused in the sectors that you see listed here. We are a seed and pre-seed fund. So if you're an early stage entrepreneur, we would love to hear from you. My email is tmravi@hivedata.com. And we've done a number of things in the industrial space also. Early company of ours, Nurego, was acquired by GE. Another company in edge. We were really a pioneer in edge computing. Foghorn was acquired by Johnson Controls. In addition to Geminis, we have another great company, Zage Security. So either if you're in the industrial space or broadly in any of the other areas, please do reach out to me. Next slide, please. And so in addition to the Hive here in Silicon Valley, which covers North America, companies based in North America, we have separate entities, the Hive Brazil based in Sao Paulo, Hive Southeast Asia based in Kuala Lumpur, the Hive India based in Bangalore, and later this year and early next year, the Hive Saudi Arabia and the Hive Europe. So if you are an entrepreneur or a corporation in another part of the world and would like to reach out to us, please do reach out to Olivia and myself. With that, next slide, please. With that, I'd like to introduce Greg Fallon. Greg Fallon has been in this domain for a large part of his career. He has been an executive at Ansys, at Autodesk, and now is the CEO of Geminis, a portfolio company of the Hive. We'll have questions. Please feel free to ask questions using the Q&A button. And Greg will reserve some time towards the end of the conversation to make sure that the questions get answered. With that, I'll hand it over to you, Greg.
Yeah, thank you so much, Ravi. And thanks everyone for joining us on the panel. Models will run the world, but hold the data. So as Ravi mentioned, I'm CEO of Geminis.ai. We're a physics-informed AI company. You'll learn a little bit more about our technology as we go through the talk. We have two esteemed panelists with us today, Doctors Jose Celaya and Alex Gordetsky. They'll have a chance to introduce themselves in a minute, but I thought I would take a step back and talk a little bit about myself, my connection to the topic, and tee up today's webinar. So going way back, when I was a kid, I spent long summer days on Long Island Sound on my grandfather's sailboat, daydreaming about air flowing over the sail. So I was a total nerd. I got really captivated by the eddies behind the boat. And I wanted to know what it was doing, what it would look like. And it was that experience that drew me to my graduate work in fluid mechanics and eventually landed me at a startup in the mid-1990s named Fluent. Fluent eventually became Ansys, which is now one of the first engineering simulation companies to introduce technology that fundamentally changed the way products are designed. They employ sophisticated simulation methods that create models that tell us whether or not something will work before a physical prototype is made. Fast forward to today, and the market for tools that create simulation models continues to grow in the mid-teens, and it's projected to exceed $40 billion by 2030. Simulation, while it's an amazing technology, has a few drawbacks and challenges. One is time and expense. Simulations often involve long solve times and lots of compute power. In some cases, a simulation run can take weeks on thousands of CPUs. The second is reliability. With most simulation approaches, a solution isn't guaranteed. Solutions can diverge, and often the reason isn't known. The third is accuracy. With most simulations, it's extremely difficult to know how accurate a given solution is. But if you were able to overcome these challenges, you'd be able to go beyond asking the question, will a design work, and be able to ask, what is the configuration or settings to achieve optimal performance? It'd be like going to find a good answer to finding the best answer, and it would drive the primary application of these tools from designing systems to controlling their operation. The alternative to simulations in driving intelligence in industry is machine learning applied to large data sets. And machine learning, while impactful, also has technology drawbacks. Because the technology is based on identifying trends in data, it needs data and lots of it. Data that isn't always available, and when it is, can be difficult to manage. The second drawback is models created this way are difficult to update. If something changes, you often have to recreate the entire model. And unlike with simulations, which are based on some sort of first core principle, it can be really difficult to explain answers coming from data-centric machine learning models. And just like simulation, model accuracy is difficult to quantify. But perhaps the biggest challenge to machine learning approach is the outcome. By deploying machine learning on large data sets, you can only identify a solution that's as good as the best you've ever done before. There's no way with these techniques to easily identify better, let alone optimal solutions. We're here today to explore the possibilities to overcome these and other challenges with new mathematical techniques that are referred to as physics-informed AI. that combine engineering simulations with measurement data to create AI models that run thousands of times faster than traditional simulations and offer a host of benefits like quantified accuracy and the ability to self-update as new data becomes available. So I'm going to turn it over to Jose Celaya. Dr. Celaya, if you would tell us a little bit about yourself, what you do, and the connection to the topic. Jose, I think you might be muted.
How about now? Good day, everyone. Thank you for the invitation, Greg and Ravi. My name is Jose Celaya. I currently work for Schlumberger in the Software Technology Innovation Center in California. My professional background is, quite diverse. I started as a control engineering academically, studying control engineering, process control, and then I came to the U.S. to grad school, focusing initially on getting a master's on electrical engineering with focus on control and AI and optimization. Then moved to another department and got a master's in operations research and statistics, and eventually PhD in decision sciences and engineering systems. So for me, it's relevant because I've been through several disciplines and I have had the chance academically to go deeply into pure model environment, then go into the statistics environment, and then back to the modeling environment and forth. So academically, I have a great connection with what we're trying to discuss here and where we're going. In terms of my work, long time back, I started computer integrated manufacturing group at my university, which there we work on re-engineering systems and manufacturing processes, and got to work a little bit with control and a little bit of automation. During my PhD, I was an intern at GE corporate R&D in the Industrial Artificial Intelligence Lab, and then a contractor. There I got to work on the early days of prognostics and health management for aircraft engines, inspection and classification of defects in all pipelines through ultrasonic data. That we can think about a deep learning application today will be great for that. And also on multi-criteria decision-making tools for real estate. After that, I joined NASA Ames Research Center here in California. I was a founding member of the Prognostic Center of Excellence. There, we worked for close to 8 years on setting up the fundamental research of what is known today as model-based PHM. We have obviously motivations in aerospace and aviation safety, and we explore a lot of what a model can do, and then got to see the limitations of models and how to bring data in order to enhance reasoning and do better forecasts about events that are to happen in the future. For the last 7 years, I joined Schlumberger Software Technology Innovation Center. I currently lead a technical area. I have teams that focus on applications of machine learning and data science to our industrial systems, team that focus on NLP and unstructured data, and also a community of principal scientists with efforts on NLP, IoT, edge intelligence, robotics inspection. So my job here is to look after innovations in the AI domain. The particular challenge that I'm tackling with my team in the last 2 years and moving forward is how do we take better advantage of the AI ML revolution? At the same time, we employ the vast knowledge of the domain, simulators, models of every kind that is very unique to a Schlumberger, and then use that together in the best way possible to develop new workflows for our customers that are rich and focus on data, but also honor some of the knowledge that we have about how our systems work. So that's a big challenge for us. So this topic, I believe, is at the core of it. Thanks.
Yeah, thank you, Jose. Alex, would you share a little bit about yourself?
Sure. So hi, I'm Alex Gordetsky. I'm currently an assistant professor at the Department of Aerospace Engineering at U of M at University of Michigan in Ann Arbor. I got my PhD at MIT in computational science, and that's kind of where I really started on this merging of models and data and analysis techniques. I work primarily on decision making under uncertainty there, and I developed algorithms to do everything, for instance, from soft sensors in wells, working with BP, to stochastic optimal control of quadcopters, enabling them to have agile flight, agile maneuvering. My focus is really kind of algorithmic research, and this has tied into throughout my career. After MIT, I went to Sandia National Laboratories in Albuquerque. Sandia is very famous for having to simulate very important things without the ability to test them, and so they really kind of are involved in pioneering the application of computational techniques merging with sparse data that's available in order to make predictions and really under uncertainty. And there I focused on, again, developing algorithms to enable uncertainty quantification, optimization under uncertainty. After that, I came to the University of Michigan. I've been here for 4 years. I work still broadly in the area of decision-making under uncertainty, developing algorithms for instance, optimizing things where you don't know exactly the conditions in which they're going to be operating, understanding the range of possible predictions given imperfect knowledge about a particular system. My projects have been funded by DARPA, DoD, DOE, NASA. I typically work with applications experts to enable them to do high fidelity analysis and design and control of anything that they would like to do. And I kind of like it working on the algorithmic side because it exposes me to many applications. I've worked on things from designing nozzles of autonomous combat aircraft to stochastic optical control of quadcopters, real-time prediction in automotive systems and transmissions, simulation of quantum chemistry systems, design under uncertainty, and uncertainty quantification for electric propulsion in space. In general, I just enjoy working on, on the computational science side, where we combine models and data. We can explore many different things about the world that are not possible in pure experimentation. That's about it.
Well, thank you both. You have incredibly impressive backgrounds. We're lucky to have you here. So let's get into the panel and talk a little bit. Let's first start at a high level. And Alex, I'll ask this question of you, and then we'll immediately turn it over to Jose. But just in general, what types of problems do you see industrial companies wanting to address with artificial intelligence?
Well, a lot of the problems are kind of that I see are related to digital engineering, but throughout the life cycle of a product, from all the way from design, manufacturing, operations, and control. One of the kind of targeted application areas that's emerging now, it has been around for a while, but it's emerging now with AI and computational advances, is the idea of digital twins. So so the question there is really, can you run a model and a simulation model alongside a physical asset and be able to use it to make predictions about what different decision-making strategies could be? For instance, to improve lifetime, or to perform predictive maintenance, or to optimize performance. And these kinds of strategies require, running a model faster than real time, assessing its uncertainty. So that means running it many times to evaluate predictions, and then also taking data that's coming off real system that we have sensors for, and updating our model, because all models are wrong, and we need to constantly update them to get new ideas, to get new and better predictions. More generally, kind of this idea of a digital thread is emerging as well. So we don't just want to do it during operations, we want to do it through the whole life cycle, as I mentioned.
Yeah, all right, thanks, Alex. Jose, to you, I mean, where do you see problems in the industrial space that are appropriate for AI and where companies can derive value?
Yes, I think in general, everything that Alex mentions resonates a lot with me and what I observe here at Schlumberger and in other places. Thinking first about AI as purely as ML, what I think it can enable us is to do a different kind of optimization in our business decision systems than we currently do. Like, for example, we in Schlumberger have embarked into the Industry 4.0 revolution. We have been making a lot of investments and development of technology on instrumenting or heavy assets, big machines, instrumenting them better, IoT enabled, edge computation, adding intelligence. So for me, we are observing the work now better and faster. We need to optimize better. beyond what we traditionally optimize. So in order to do that, a clear application is a digital twin, but also another application that concerns us a lot. How can we build a fast approximations, say with machine learning and data science, of systems and processes that allows us to optimize beyond what we usually do. Like simple example will be on my understanding of a chemical processing plant. There's obviously optimization there that is done with a linear program, and there are a lot of assumptions. That optimization is run probably once a week or once a month. Now, if I have a chemical plant now over-instrumented, and I'm observing everything that is happening, I can observe the economic world around it, change it. I need to be able to optimize dynamically and faster, right? Not every week, not only with a linear program with a lot of assumptions, but with more integration of what's really happening there. So for me, I think that's a big thing to work on, or exciting thing.
Thank you, Jose. I love the example. So let's turn a little bit to how people are trying to solve these problems today, and then we'll talk a little bit about next generation techniques. So Alex, to you, what are the most common approaches to these problems today, and what are their limitations?
Sure. So kind of building off the example that Jose just said, well, you have this data coming in and you want to start making decisions, optimize on the fly. One of the biggest issues is the actual computational expense of running predictions that involve the optimization. And this kind of lends to the approximations that Jose talked about. For instance, if you're going to run a physics-based model purely built from first principles with no kind of where data maybe is used just to update some parameters, these models are typically very, very expensive to run, especially to perform optimization or decision-making on the fly. Alternatively, if you're going to run a data-driven model where you're going to do pure ML, this is not going to be able to extrapolate to things that you haven't seen before. And kind of the problems in these sort of space are different than standard or traditional machine learning problems. Because, for instance, in text to text prediction, you want to predict the next word or paragraph. You have data, and that data is pairs of previous words and paragraphs and next words and paragraphs. In these sort of applications, we have censored readings on some things, and we want to predict other things that are completely unrelated. Purely machine learning or data-driven models don't give that extrapolatory power. What we need to do is we need to combine them. For instance, you get measurements of temperature, you want to make predictions on pressure. You need to be able to combine kind of purely data-driven machine learning approaches with the physics that enables you to extrapolate. And these sorts of things are kind of emerging, but challenges still remain to make them scalable and fast enough for the sorts of optimization decision-making that Jose was talking about.
Yeah, Jose, do you want to elaborate on that at all?
Yeah, I think so. Well, I can think of another example. For example, a typical for us will be a huge compressor in production of hydrocarbons, and very critical to that with a big economic impact. So we want to be able to optimize and trade off in a space that is beyond what we do right now. So if we think about the compressor failing and reliability aspects, minimizing downtime, the way we have to do those things, though data-driven and experience-driven, usually leaves a lot on the table. Now, if I'm able to observe that compressor, I'm able to employ the knowledge that I have about computational fluid dynamics and on how that compressor could operate. Then in principle, it can enable me to have a new environment when I can trade off the life of the compressor with economic input, right? And then as the world changes around that production system network, it has a lot of potential for us, to have a better economic outcome, to minimize downtime. I can also think on the same time about something that is critical to safety and the environment. If I have perhaps a membrane that is a filter, right? I can have a rigorous maintenance or replacement schedule, but I will be leaving likely a lot on the table in terms of the life of that membrane, and it is an expensive one. So us being able to optimize that dynamically and being able to trade off in a space with enough knowledge, fundamental knowledge that can tell us, you are still optimizing, but we are not putting any stress or risk in our ability to have a safety event of an environment event. So all that is critical, right? And so the issue right now, I think, if I have to try to link a little bit to what Alex said, is that we have knowledge in sort of a silo way. So a model for a particular function, a model for a particular control function, a model for a particular reliability function. But what I want to have is, as we observe these assets real time, I want to be able to optimize not individually at different timescales, but all together. And so in order to do that, I need a way to have these computations be faster.
Yeah.
Hopefully that I'm not going too into the weeds, but a couple of additional examples there.
I think it was perfect, Jose. Thank you. So let's talk a little bit about some of the emerging technologies. Alex, why don't we start with you and your research and the techniques that you work on?
Sure. So, there's a couple of threads here. Maybe I'll start with the kind of the computational challenges associated with approximation. And I view everything as a kind of a computational challenge where we really need to do real-time decision making. And when I mean real-time, it could depend on the application. If you need to make a decision once a day, but your code requires running for 4 days, that's still a problem, a computational problem that you want to work on. And typically we know what we want to do. We want to run the code 100 times to assess all possible outcomes and then be able to decide how best to operate it. We just really can't afford to do that. And so a majority of the research kind of that I pursue aims to computationally alleviate this burden. And there's multiple ways to do this. For instance, one way to do it is you have some really fancy first principles physics model. And yes, it can predict everything, but it takes a really long time. But maybe you can sacrifice some things that you want to predict, only predict a couple of things that are really relevant for decision making. For instance, range of an aircraft or lifetime of your physical asset. And you can do this by taking away some of the physics and replacing them with simpler models that you learn from data or from databases of simulations. So this kind of data augmentation of physical models tries to get the benefits of both worlds, where we take physical models and they really allow us to extrapolate, and then we take data and we can infer things within those models that allow us to predict quantities that we're interested in, perhaps not everything, because again, predicting everything is just computationally intractable. But in this way, we merge kind of AI and ML in order to, with physics, in order to maintain extrapolation along with computational accuracy. Another kind of thread for computational efficiency is the idea, and this is an emerging idea, of multi-fidelity. And so this kind of an idea is the following. You have a really fancy model that takes days to run, but you also, when you've developed your model, you've obviously gone through some sort of development cycle, and you've come up with, let's say, 5 different models of varying fidelity, but are cheaper. And maybe the cheapest one you can write down on the back of the envelope and run. And although these models are very simple, they're wrong, but they sometimes have the right qualitative behavior. And it turns out that you can actually combine qualitatively correct models with high fidelity models in a way, and fuse the information together to make predictions with much lower cost, but with the same amount of accuracy. So again, instead of running a very, very expensive model hundreds of times to assess its behavior, maybe you can run it only 5 times and run the simpler models 100 times and fuse that information together. So these are kind of 2 threads that are emerging in the research to kind of combine AI and physics together to really deal with this approximation or computational burden.
Yeah, thank you, Alex. So Jose, next to you, just to expand on Alex, I'd imagine that in your position, you've got exposure to a broad range of machine learning technologies. What are you seeing that you think is especially promising?
Well, I think the topic that we're discussing here, right, being able to leverage the domain knowledge that we have in a smart way. So we have seen or done some work where we can surrogate certain physical model to the simulation data and then building our own. So we believe to some extent that works, but it is very knowledge intensive, right? So what I'm excited about the technology, particularly instantiated what Alex said, is I want to be able to have better tools that allows the scalability of the modeling function, right? We live also in my day-to-day work in an area where it's all about software, and we tend to get confused or misled ourselves thinking that everything is about software data and computer scalability, but it's really not. What I really care about is modeling function and scalability, so that the technologies and the ways to see the world, the modeling world that Alex was describing, I think opens up a lot of opportunities for us. I see it easily going, not really as a scientific research, but going into technology that we can use, toolboxes that our engineers can use to build new ways to optimize their operations. So I think, from that perspective, I'm excited about that. In more philosophical point of view, I strongly believe that we're just getting started about exploiting more computation. I think we have done great work on exploiting the fact that we have now more data, and then machine learning applications in many industries, and data science application is a great proof of that. But I think I'm very excited to see how we exploit also the large amount of computation we get in the cloud in a distributed way, and computation available ubiquitous in many places, and take advantage of that from a modeling function point of view. So I see in a way correlates to a lot with what Alex was mentioning.
Jose, you talked a lot about scalability there of the models, and you and I have had a lot of discussions about creating faster physics-based models of systems and systems of systems. Can you talk a little bit about scalability and what you mean?
Yeah, for example, if I put my hat as a PHM engineer at a Schlumberger, and I am to build a remaining useful life estimation for a particular pump, right? I can spend some time and use some knowledge of the models available, or a lot of machine learning to create a model for that, and build a modern remaining useful life estimation solution. So that will take me quite some time, but it is doable, right? But we don't want to play there. What really the value proposition for us is our ability for me to have that estimator tuned for thousands of that particular asset. And those assets are different stage in their life. They are in a different environment. They are used at a different rate. And all those three things affect the quantity the event that I want to forecast in the future for them, for the business to make more money in a safer way. So there's really, that scalability is not available, right? It's just we will have to do from scratch 1,000 times the same thing in hand tune. So I have no good ways to trade on that space, right? So that's one of the aspects that I mean. On the other side, I want to compose models of larger networks, right? Again, we do a lot of, let's say, PID control on different things. So obviously we start with a model there that is basic for a particular function. But I want to be able to compose a functional model of a larger system, again, because I want to optimize not on silos, I want to optimize at different layers. That scalability, I think, is up and coming. We see it, for example, I got to see it a little bit at NASA, model-based systems engineering is sort of focuses on that. How do you do those systems engineering function in a model-based way of a larger critical asset? So that I think that is what I would like to see coming our way. And right, I can keep talking about this. So let me stop there, and then you can guide me to whether I answer the right question or we can go somewhere else. Yeah.
That was fantastic. Let's talk a little bit. So Alex has outlined some new technologies having to do with reduced order model creation and multi-fidelity scenarios. Alex, when you think about this and you look through your research, can you elaborate on your own experience in terms of perhaps some of the challenges that people are running into as they're taking these techniques from the lab and deploying them in the industrial space?
Sure. I mean, I think one of the major challenges, actually, with any kind of ML-based approach, is verification and validation of your model. So, as soon as you kind of start introducing data, you talk to application experts, and all of a sudden they're saying, "No, I can't trust these predictions. They're purely regression fits." And I think there's multiple questions buried in this. So I think you have to, for instance, start attributing the risk of certain decision making. So you don't just have models, but you're going to make decisions based on them. So I think one thing that you need to start that kind of we need to understand and start looking at is what is the risk of making wrong decisions when you use data based models. Another related question is kind of where have you validated these models on which types of data, and how far away is that from the regimes in which you want to predict? Because often the whole point of incorporating physics-based models and not doing purely ML type stuff is because you want to predict in ways you didn't see data for. That's kind of the challenging, the more interesting questions. So you need to be able to calculate what's the uncertainty of your predictions, and you can't just give one answer anymore. And people need to be comfortable with having kind of errors and misunderstood, somewhat, let's say, not perfectly understood predictions. But also we need to verify that everything that we've implemented is correct, bug-free, that we've trained in proper ways. So all of this comes together to kind of talk about, to ensure that we've implemented what we think we've implemented, that we validated on data that we've seen, that we provide probabilistic predictions. And I think this is a very different way of thinking about how do we use models than currently is used, where you maybe take one model and we get one answer, and we do this offline, and then we forget about it. We make a decision, we go on. But now these models are constantly being updated. You need to constantly ensure that you are confident in their predictions. To me, that seems to be one of the biggest challenge to at least convincing more traditional physics informed people that combining data and this to be able to do this more advanced analysis at a faster rate is necessary.
Yeah, thank you, Alex. So Jose, a question to you, and this has come up in different forms in the chats as well. But so the application space for these types of techniques that Alex is describing is pretty broad. And you've had a fair experience of seeing applications across NASA, Schlumberger, GE, in your academic research. What types of problems do you think industry should tackle first with these new techniques?
So it's a tough question. I don't think I have the wisdom to answer it straight. So let me try to decompose it or qualify it. Right. So if we're talking about heavy industries in a company where you have assets that you design, deploy, and maintain yourself, so it's very easy to see that from a business perspective point of view, the prognostics and health management on a large scale or fleet type of scenario is sort of a no-brainer, right? It's very easy to see at high level the value proposition. There are some tricks there or difficulties in order to bring it down to engineering requirements, but that is particularly an area that I think we have seen some work done in other industries, but doing it at scale, I think this will be the great technology or application for a technology like that. So I don't know if I should clarify what it means, right? And prognostics and health management for me is just think of a machine and in terms of its reliability and life. Something may be off nominal of the machine, then we do have anomaly detection algorithms that can tell you something is off. You can go even further and have diagnosis and sort of basically identify what is wrong and how wrong it is. And the prognostics part is sort of predict, right? It's a forecast based on how you want to use it in the environment and so on and so forth, when things are going to fail. So you can start trading, right? Not only when you're going to maintain, but you can train service quality in your, or uptime contracts and so on and so forth. So I think that doing it at scale for, let's say, if we think about valves in the surface or hydrocarbon production, I don't know how many thousands, hundreds of thousands of valves are there in the world right now, and they're critical to production, right? You can think about they're critical to safety in the environment, right? So we really do care, to know about where they are in their life, right? So that's one thing. So again, bias to where I've been in my life and what I see here, and right. That's one example, right? I can think of more if there's time.
Yeah. Oh no, thank you, Jose. So Alex, back to you. So I'm sure that you see a wide range of applications in your research. Can you elaborate from your own experience? Are there applications for technologies you're researching outside of the traditional industrial space? So, I think a lot about traditional energy problems like wind turbines, like extracting oil and gas, perhaps life cycle of turbine engines. But if you think about the traditional mechanical, electrical, and fluid dynamics space, are there other industries where you think these types of techniques make sense and use cases, perhaps in operations or other areas?
Sure. I mean, the challenge with extending it to kind of other areas, let's say, as opposed to the ones that you just mentioned, is that the ones that you just mentioned have well understood physical behaviors. And so they've built very well understood physical models. If you're going to transfer to, let's say, I don't know, finance or other prediction type of things, you're going to have challenges because there's less ability to extrapolate since there may not be first principles models. One kind of way to do this, though, is of course to get more data. So if you want to be able to extrapolate to predictions, finance or demand, supply chain demand, you're going to need more data, and you're going to need to be able to build more models. I think there's definitely some opportunities there. And the opportunities there will have to be, of course, constraining the model prediction. So you might no longer have physical laws there, but you need to think about other invariants or behaviors that you want your system to include, and that could kind of stand in place of the physics. I mean, there's a lot of other areas where I work in where the system is too complex that even these simple models, it's not just the fluids model, it's not just an electromagnetic model, it's some combined model. I think this provides, for instance, like in the electric propulsion systems that I work in, there you really don't know what the right fidelity is. Depending on what you want to predict, you have different things that you might want to predict. So kind of these areas where maybe you can run some models that are very high fidelity, but you don't know exactly what you want to predict, but you can get a database of many things, or that you have a lot of data for that you can start trying to build models. And these types of applications, I think, are amenable for these kind of mixture of physics and AI techniques.
Yeah, thank you, Alex. Jose, is there anything you want to comment on that? Go ahead.
Yeah, so hearing Alex, I got a couple of light bulbs, but from back from grad school, there's this area of modeling that is not about machines, that is systems dynamics, right? Either economists or people use that, right? And basically, there you can interconnect different aspects, either economics to some other sort of dynamics of behavior, even model a pandemic, let's say, with a mechanistic system dynamic model. I see no reason why technologies that we're discussing here cannot really revolutionize there too, right? Because there's a concept of a dynamic model built by an expert and a community of experts. There's also an element of data being observed in runtime about a particular a macro or socioeconomical behavior or economics purely, right? There's the traditional operations or statistics way will be to revisit, to return, to recheck core assumptions. And if we have a way to computationally do that, right, update those models on the fly to honor data, but also to honor the first principles that were put there on the systems dynamic model, it has to be a game changer there too, right? Or at least allowed to do things faster. I don't know. Some smart people in business will think about how to exploit that.
Yeah, all right. Well, thank you, Jose. So we've got a bunch of questions that are coming in through the Q&A chat. Um, Let me bring up a few and let's see if we can tick one of these off. There's
Mhm.
one here that I'm looking at. What do you think is the scope of physics-constrained data-driven models in the industry, where some of the physics from governing laws is embedded in the loss functions? Are these being implemented yet? Either of you want to take that?
I can give a little bit of a Schlumberger perspective. Yeah, I think on the mid technology readiness level, we have done things like that in a Schlumberger to a great success in some places. Right, but Schlumberger is very wide in terms. You can think about 20 companies into one, right? So I cannot tell you the details, but yes, that is happening. We also have observed limitations of that. For example, in my team, we have a project that it's about drilling, right? And in drilling, you have the dynamics of the earth downhole. You have the dynamics of the drill bit hitting the earth, the dynamics of your drill, and then the dynamics of the driller and influenced by economic aspects at the top. So these just three systems that are connecting each other. And there are things that we would like to predict there, adverse events that we want to anticipate that are impossible to do individually on these three different dynamic systems, right? It has to be all together. And we have a very hard time putting what matters in a loss function, right? Maybe we will get smarter or someone will get to do that better, but we see that as a limitation, right? To do that at the loss function. So two examples, right? Clearly one success one and another one we have found it extremely hard to do that.
Yeah, fair enough, Jose. Thank you. Here's one. I think this is for you, Alex, but I'll leave it to Jose as well. How big of an issue is missing, sparse, dirty, or even too much data in model function scalability and AI augmented simulation?
Sure, I can tackle that. I mean, if you're going to be talking about, let's say, sensor data coming off from measuring a physical asset, I think it's going to be quite sparse and quite dirty. The reason is because your model of the physical asset maybe includes things that you don't just want to sense. So we do talk about observables, for instance, things that you can sense, or can you predict the future data? But kind of the real point is that you want to also predict things that you don't have sensor readings for. And in any time you're going to be running a realistic system, you're not only going to have sparse and noisy data, but your sensors might fail. How do you recognize that happening? And so I think in general, it's going to be a big issue that your methods need to be built in to account for. I don't think there's going to be, in contrast to kind of more classical ML cases, the data is not going to be as clean. There's going to be for sure biases in the data that you don't know ahead of time, and they might be hard to learn as well. It's going to be sparse. It's going to be noisy as well.
Yeah, no, thank you, Alex. This is another one that, Alex, I'm going to push your way because I think academically you might be closer, but Jose, I'll let you answer. This came in from a user that says, our experience has been that pins work well for simple geometries and problems. Scaling them to real world problems remains a challenge. NVIDIA modules show some success. Any comments on that? And so the first question I'd ask for you, Alex, is to maybe differentiate between the methods you described and pins, and then maybe talk about what you know about pins.
Sure. I mean, I think this is also what Jose was alluding for when he tried at Schlumberger. But I mean, this is basically, I mean, there's many variants of pins, but in the classical case, you encode your physics as in a loss function, and then you parameterize your solution with a neural network, and then you just minimize the loss function, and therefore you fit the data. This is kind of at a very high level what this so-called physics-informed neural network is. In reality, I mean, it's really very much like any other solver technology, except now we're using neural networks. And it's actually a lot easier to implement, maybe because of the very good investment that the tech space has done in things like PyTorch and TensorFlow that allows you to do that. And that's kind of maybe a solution to the solver problem. It doesn't really address cases where, let's say, you don't have enough data to fully identify the full physics that you want to solve. So you kind of model error. You need to embed model error because you don't know the full equations. So this is kind of a different realm of work that pins don't address. But pins do try to address the ability to get, let's say, fast, rough solutions to some governing equations as well. And certainly they'll improve more as the computing gets more, essentially as the machine learning back end gets more, and they're certainly easy to implement. But I think they do remain, they still remain quite challenged, essentially, by what Jose was talking about previously.
I think what I could comment, there's still a little bit of time, is it makes sense to think of this problem about, for me, what is your modeling function, right? So if I put my hat as a physicist or a mechanical engineering PhD, and I'm trying to do a model to the best fidelity possible to a certain reality or physics, right? Definitely thinking about pins, they are early research stage, right? What we can observe right now is, this is cute finding, right? It makes sense to continue to explore from a scientific discovery point of view. It makes sense. So, but if you want to think of that for a practical application, and you want a pin model that covers everything, different environments, operations, something that you will describe with partial differential equations, multiple dimensions, is a complicated thing. Now, on the other hand, in many industrial applications, you don't necessarily need to have the physicist or mechanical engineering PhD model target, right? As Alex mentioned, is one of my favorite things, or all models are wrong and some of them are useful. If you can constrain your modeling domain to a particular operation regime, to a particular set of environmental conditions in temperature, to a particular input-output regime, right? And if you're talking about a system that is well described with ordinary differential equations, right? Like, water recycling system is something that one of my colleagues had worked on. I'm quite confident that there, with a little bit of push, you can really make something with pins, right? And particularly now that there's a push to describe things on frequency domain there. But again, now you will have to talk yourself about what is the value of doing pins if you get a good chemical engineering, they can build you the model to do that. So at some point where they start working, it seems to me that it is non-science. It's just we tend to forget. The word didn't start 5 years ago with deep learning, right? It's really, we have a lot of science and engineering that we tend to forget nowadays. So sorry, I'm going too philosophical, but I wanted to comment on that space.
No, that's great, Jose. Okay, here's another one that just came in. How should we think of the various models with multiple fidelities? Are they meant to be run based on how fast you want the result? Or would you employ them in a hierarchy to navigate, evaluate based on intermediate results?
So I think this is a great question, and there's multiple kind of facets for it. In an ideal world, what you would do is you want to say, I want an answer, and this is my computational budget. And the system would figure out how to best run your multiple models in order to get you the answer. This is kind of what we're working towards when I talk about multi-fidelity. Now, this system should be automated, and it could include choosing which one to run in order to get a particular result. It could also include the ability to say, run the lowest fidelity model. Is that good enough? If not, continue, correct, things like that. So this latter case is maybe kind of finding the appropriate fidelity to run. And the first case that you were talking about was saying, how do you use the whole ensemble to accelerate? And the kind of what we're trying to work towards is a more holistic viewpoint where these are all the information sources. Here's the high level question. I want to predict when you do this, when you run it in this operating regime, what is going to be the, the range of predictions. Now figure out how to best use the resources that you have, which would include, again, both of the options that you've described.
Yeah, if I may comment, what I would like to see in the next few years is that we start talking about that. We talk nowadays about the way we talk about other computer systems. I started to put these thoughts about what we really need is, I think, is something like software-defined models, where I can programmatically define what I want on a model and get it built for me. So if I'm talking about electronics, I can programmatically define, I want electronics 101, voltages and currents and power is what I want. And I want certain forward model computation speed, and I'm willing to tolerate certain level of uncertainty, right? And be able to programmatically get that built for me so I can optimize and use. In the same way, I can say, well, I want something more complicated. Really, temperature is an issue. So I want this model to include temperature. Now it takes you away from electronics 101 to electronics 201, right? And be able to. So I don't know. For me, in order for heavy industries to fully realize Industry 4.0 financial value, right? All the investments on IoT and connectivity and cloud, or engineers in operation in a knowledge-intensive world, will need to have the ability to request models at different fidelities for different purposes on the fly. And we have to hire a data scientist or a mechanical engineer, a double E PhD, to be able to build those every time. We're not going to scale up, right? So putting a computer systems answer to that, yeah, we want to think about this as software-defined modeling function.
Yeah, thank you, Jose. So we've got 3 minutes left, and I think we have time for one more question, but we'll have to be brief. I wanted to bring this one up because I think it's a really good question. And this is coming from an audience member. What are the dimensions to map use cases? Approximate solution, but quickly versus accurate solution, but slowly, data-driven versus physics-informed, etc. And so maybe this is to you, Alex, thinking about, how do you decide which techniques to use, and what are the dimensions that you consider?
Sure. I mean, this is something that any sort of modeling decision, it can get quite philosophical. What is the fidelity you need? How do I build the model? All this. I think that the only way to really decide is that you have to go through the decision-making aspect and see what the actual final reward is, because it really doesn't matter what you choose if they both give you the same outcome, same final decision and the same final reward. I don't think that there's any other objective metric. So I think that essentially you can use a lot of your intuition, because maybe you can't evaluate the reward for the decision yet, and there you can you use your intuition. But I think that as you start building these systems, it needs to be more than just modeling. You need to wrap in the effect of the decisions, and you need to consider the costs of making a certain decisions based on what a model gives you. And that needs to be included within, again, this digital thread that I was talking about, because otherwise, if you're only focusing on the modeling and trying to predict, it might be difficult to, you can always skew things to say that you're doing the right thing. But if you actually measure these things, are you making different decisions or anything like that, things often change. So I think that's really the only way to make objective decisions about these sorts of questions.
Yeah, well, thank you, Alex, and thank you so much, Jose, and thank you to our audience. Ravi and Olivia, I'll turn it back to you.
This was a tremendous conversation, and there are still many sort of questions that haven't been answered. So we should plan on doing a part 2 of this event. And I especially want to thank the audience for being so engaged and for the great questions. Thank you, Greg, Jose, and Alex for participating. Olivia?
Thank you everyone so much. And then just as a quick reminder, we do also have our August 17th webinar with TIBCO, Kamesh, and then Blockstream. So we did go ahead and put in the registration link in the chat. So hopefully we'll see you all on the 17th. But with that,
and we hope to do in the fall our first post-pandemic event in person. And so we look forward to seeing everyone in real life soon. Thank you all for joining.
Well, thank
Great.
you, Jose,
Thank you,
Alex,
everyone.
and Greg again.
Have a good day. Thank you.
Thank you. Have a good day.